Today we're working on the review for the Chapter 17, 18, and 19 test that's coming up this week. Question number 1 asks us to identify the sine, cosine, tangent, cosecant, secant, and cotangent of the reference angle theta. So remember, it's helpful to start by circling your reference angle. And then for this one, we're finding all 6 of them. So I'm going to go ahead and label. The 5 is opposite or across from the theta that's indicated here. So for this angle, 12 is adjacent to that, and then the 13 is my hypotenuse. So labeling those on the picture will help me when I go through and set up these ones over here. Remember, I'm going to use the acronym SOHCAHTOA to help me set them up. So from angle theta, sine would be opposite over hypotenuse. And so that's why the 5 goes in the top and the 13 goes in the bottom. Cosine would be adjacent over hypotenuse. So 12 over 13. And then tangent would be opposite over adjacent, so 5 over 12. Cosecant is the flip of sine. Secant is the flip of cosine. And then cotangent is the flip of tangent. And so you just take these 3 fractions that you find over here and you flip them. Question number 2 on the review gives me some information. So it says the sine of angle theta is equal to 7 over 8. And so this is my reference angle theta. A triangle helps you with this picture, or drawing a triangle helps you solve this problem. It's not a required step, but it's recommended. So sine is opposite over hypotenuse. And so no matter which way you draw your triangle, the 7 should be opposite or across from whichever angle you label as theta. And then 8 should be on your hypotenuse, which is the side of the triangle that's opposite from the 90-degree box. We're being asked to find cosine of theta. And so remember with SOHCAHTOA, for sine we used opposite and hypotenuse, but for cosine we need to use adjacent and hypotenuse. So we need to solve for this side of the triangle over here that's missing. To do that, I'm going to use the Pythagorean theorem. 7 can go in for your A or for your B. But your c squared, the 8 has to go in for your c because that's your hypotenuse. And so to solve this, I'll minus the 49 from both sides. And so going through and solving it amounts to solving this. When I take 64, take away 49 gives me 15. And then to solve for that missing side of the triangle, I'll take the square root of both sides. So I'll get that the missing side of the triangle is the square root of 15. And you do want to leave it in its square root. You're not going to take it out from under its square root. I was given sine, but I wanted to find cosine. And so for this one, the cosine of angle theta, remember cosine is adjacent over hypotenuse. So the 15 comes over here, the square root of 15, and that becomes my adjacent side. And so for cosine, I'm going to have the square root of 15 in the top and then 8 in the bottom. So adjacent over my hypotenuse will be the answer for that question. Questions number 3 and 4 have the same directions. They want us to solve for the missing side of the triangle, and it indicates that we should do so using a calculator. So for 13, I'm going to follow the pattern. So I'm given an angle, so I'm going to circle my reference angle. Y is opposite, and then 5 is the hypotenuse compared to that 28-degree angle. So that's how I know I'm going to use sine for this one. Remember, when you're doing SOHCAHTOA, and it doesn't hurt to keep writing it to reference it, sine will be opposite over hypotenuse, and so that's these 2 that I have here. So for this one, I'm going to say that the sine of 28 degrees is equal to, and then it's opposite over hypotenuse, so y divided by 5. I'm not going to touch my calculator yet because I want to get the y all by itself, and I just want to type it into my calculator once. So to isolate the y, I would times both sides by 5. And so for this one, y is going to be exactly equal to 5 sine 28, and then you need to type that into your calculator. Make sure when you get ready to type this into your calculator, however, you want to make sure that your calculator is in degree mode to start. So on your calculator, remember anytime your calculators reset, they always reset in radian mode. So you're going to want to press mode, go down to radian, and then switch it over to degree. And you're going to have to see that it changes to degree up here. So that's how you know that you're in degree mode. You're going to have to switch back and forth on the test, so you want to make sure that you're confident with how you switch. let's see for this one. So 5 sine 28, and I'm in degree mode, so I know that I'm good. The directions for this question say to round your answer to 1 decimal place. So rounded to 1 decimal place, here y is going to be approximately 2.3. And then the directions for question number 4 are the same. We already have SOHCAHTOA written down up here, so we don't need to rewrite it. I'm going to circle my reference angle. The x is the adjacent side, and the 18 is the hypotenuse. And so that's how I know that I'm going to use cosine on this one. So the cosine of 31 degrees is equal to adjacent over hypotenuse. And then I'm not going to touch my calculator yet because I know I'm going to times both sides by 18 once I have this equation set up. So x is going to be exactly equal to 18 cosine 31. And then when I type that into my calculator, double check and make sure you're still working in degree mode. It should be in degree mode unless you've changed. Rounded to the nearest tenth, it's going to be 15.4. So x would be approximately 15.4. A good way to check your answers to these questions is you remember that the hypotenuse of a right triangle has to be the longest side. So on this one, the hypotenuse was 5, and I was solving for this side, so I knew my answer had to be less than 5 or else it's wrong. On this one, my hypotenuse is 18, and I'm solving for this side. Because the hypotenuse has to be the longest side of a right triangle, you know that if you get an answer that's bigger than 18 for this side, it means you know you made a mistake and you should go back and check your work. Question number 5 starts by asking us to decipher a word problem. We're going to make sure that we draw a picture to represent what's going on in this one. A car is traveling on a road that goes up a hill. The hill has an angle of 14 degrees relative to the horizontal. And remember, horizontal means side to side. How high up the hill vertically will the car be after it has traveled 100 yards up the road? And round your answer to 2 decimal places. So reading the question for this one will help us draw a picture. It doesn't matter which way your triangle is facing, but the car is driving up a hill, so the hypotenuse should look like it's going uphill. So this is where the car is starting, and then it's traveling and going this way. So the car is traveling on a road. The hill has an angle of 14 degrees relative to the horizontal. So this is the hill, and then this is the horizontal. How high up the hill vertically, x, so I'm trying to figure out this distance, will the car be after it has traveled 100 yards, so that's 100 on that side, 100 yards up the road. Setting up the picture for this one is the first part to getting it right, and then once you have the picture set up, then you're going to want to follow your steps. The x is opposite, the 100 is the hypotenuse, and so that's how for this one, I know that I'm going to use sine because I have opposite and hypotenuse. So the sine of 14 degrees is equal to x over 100. That would be my equation, and then I'll times both sides by 100. So x would be exactly equal to 100 sine 14. Remember, you're still working in degrees, so you'll go ahead and type that into your calculator. The directions for this question want us to round it to 2 decimal places. And so typing that into the calculator yields this, rounding it to 2 decimal places, so 24.19. It's an approximation. And then the measurements are being measured in yards, so I'll put my answer in yards. Question 6 and 7 have the same directions. It says, given that the tangent or the cosine of the angle is what they are given as, it wants us to find out how big the angle is. And so using your calculators to do your work for this one, you can leave your calculators in degree mode because you can find your answer in degrees. They want us to round our answer to the nearest whole degree. So you just have to remember how to go backwards. If you already know that tangent is opposite over adjacent, you're not going to need to draw a triangle to figure out the answer to this question. You just have to type it into your calculator the right way. So remember, on your calculators, sine, cosine, and tangent let you find sides of triangles. But up here, the sine, cosine, and tangent that have the -1 up here, those are how you're going to find the angle measurements. So if this is what's given to me to find the angle, I'm going to do tan inverse 3 over 5. And so this is going to get typed into my calculator just like that. So I'll do second tangent, and then 3 divided by 5, close my parentheses. I'm working in degree mode, so I know I'm good there. So 30.96, they want us to round it to the nearest whole degree though, so it's going to round up. So if the tangent of the angle is 3 over 5, then that means that theta, or the angle that you're solving for, is approximately 31 degrees. And then same thing for this one. If I'm trying to figure out how big the angle is, I'm going to do cosine inverse. And so that's what I'll type into my calculator. So second cosine 1 divided by 3. And then I want to round it to the nearest whole degree. So for this one, it's going to be 71 degrees for theta. What's helpful about going backwards is that you can always check your work and go the opposite direction. So I'll show you an example of that here. So the tangent of 31 degrees is a little bit bigger than 0.6, and 3 divided by 5 is exactly 0.6. So that's how you can know that you did it right, because when you go backwards and you type in regular tangent with this number next to it, it gives you approximately what that decimal is. Same thing with cosine. I got that the cosine for this angle, if the cosine was 1 over 3, it was 71 degrees. So if I type in cosine of 71 degrees, and then if I type in what 1/3 is as a decimal, these are almost exactly the same. And so that's how you can check and make sure that your answer to the question is correct. On questions 8 and 9, I'm doing the same work that I was doing up above in 6 and 7. The only thing that's different is I'm being given a picture. So I also need to decide which trig ratio I'm using. So I'll circle my reference angle. 7 on this picture is the opposite side, and 11 is the hypotenuse. And so SOHCAHTOA tells me that for this one, for this being my reference angle, if I'm using opposite and hypotenuse, that means I'm going to use sine. So I choose the sine of angle A is equal to 7 over 11. Remember, when I'm solving for my angle, I'm going to use the buttons up above sine, cosine, and tangent. So sine inverse 7 over 11 is what I would type into my calculator. And the directions for this question also want them rounded to the nearest whole degree. So typing that into your calculator and then rounding it to the nearest whole degree for this one, 39.5, it's going to give you 40 degrees as your answer. So for this one, angle A would be equal to approximately 40 degrees. Or the measure of angle A, you could write it that way as well. Let's see, circle my reference angle. So on this one, the 23 is adjacent to the letter A and the 26 is the hypotenuse. And so that's how I'll know that I'm going to use cosine, because I have adjacent and hypotenuse. Now, it's probably helpful to point out on this one that you could use tangent. You could do the Pythagorean theorem, solve for this missing side over here, and then use tangent, or then use sine as your trig ratio here instead of using cosine. But it's better to just use the two sides that you're given, because then you won't make a mistake accidentally when you're calculating for that third side. So the cosine of angle A is equal to 23 over 26. So adjacent over hypotenuse. So to solve for the angle that's missing, that's what I'm going to go ahead and type into my calculator. So second cosine, 23 divided by 26. And then rounded to the nearest whole degree, that would give me 28 degrees. So the measure of angle A on this one would be approximately 28 degrees. For questions 10 and 11, they both refer back to word problems, and I can't emphasize enough how helpful it is to draw a triangle to help you solve for these. The ADA sets the maximum angle for a wheelchair ramp entering a business at 4.76 degrees. Determine the horizontal distance needed to accommodate a ramp that goes up to a door that's 2 feet off the ground. If necessary, round your answer to the nearest foot. And so reading the word problem can help us draw our picture as our answer to our question. It's a wheelchair ramp that's going up. And the Americans with Disabilities Act says that it sets the angle of elevation, or the maximum angle, as being 4.76 degrees. So that's as big as that angle can be. It says determine the horizontal distance, so that's what I'm solving for, needed to accommodate a ramp that's going up to a door that's 2 feet vertically off the ground. So this puts my numbers in the right place. Once I circle my reference angle, then I'll be able to look at the picture in SOHCAHTOA and decide what I'm going to use. So for this one, the 2 is my opposite side, the x is my adjacent side, and so that's how I'll decide for this one that I'm going to use tangent to solve it. So the tangent of 4.76 degrees is equal to 2 over x. This one's a little bit different because the x is down in the bottom, but I'll follow the same steps that we followed in our notes. I'm going to multiply both sides by x to bring the x up out of the bottom. So x times the tangent of 4.76 degrees is equal to 2. And then to solve to get the XL by itself, I need to divide both sides by the tangent of 4.76 degrees. Over here, oops, the whole thing crosses out with the whole thing, so it wasn't just part of it, it's the whole thing that's gone. So the exact value for x would be 2 over the tangent of 4.76 degrees, so that would be your exact value. I'll slide the 2 over a little bit. The directions to this question, however, say that they want us to round it, our answer to the nearest foot. So make sure you're working in degree mode on your calculator. No second tan on this one because we're trying to solve for a side length. So it's going to be 2 divided by the tangent of 4.76 degrees. And so I'll type that into my calculator and then round it to the nearest foot. It would be 24 feet. So that's how far away the ramp would need to be. So again, rounded, the answer would be 24 feet. Question 11 is also a word problem. Question 11 says, a building is 24 feet tall. At a certain time of day, it casts a shadow 37 feet long on the ground. And then on this one, they want us to solve for the angle. It doesn't matter what way you draw your triangle. You just have to make sure you put the numbers on the sides that correspond to the information in the question. And so notice that for these ones, we're setting up the triangles together because you're going through and trying to practice setting up the triangles. So for this problem, it says the building is 24 feet tall, and at a certain time of day, it casts a shadow. So the shadow is down here on the ground, and so it's 37 feet long on the ground. And they want to know what's the angle of elevation at that time of day with the sun. So I could call this angle here A, or I could call it theta. It doesn't matter how you measure it, but that's the angle that you're going to be solving for. The 24 is the opposite side. The 37 is the adjacent side. And so that's how you decide that you're going to use tangent, because tangent is opposite over adjacent. So for this one, let's see. The tangent of angle A is equal to 24 over 37. So this is where this problem is a little bit different. In this problem, you were solving for a side length, but in this problem, you're solving for an angle. So you're going to use tan inverse, and you're going to type this into your calculator so that you can determine how big the angle is. So second tangent, 24 divided by 37. And then the directions for this question want us to round our answer for number 11 to the nearest whole degree. So when we type that into our calculators, we get this, and then round it to the nearest whole degree. It would be 33 degrees, would be the angle of elevation that it makes with, that the sun, how is it worded? The angle of elevation of the sun at that time of day. On questions 12 and 13, when you're solving to figure out coterminal angles, remember that coterminal means that they end at the same place. And so for this one, you're looking for a positive angle that ends as the same place as 155 did. So an angle that ends at the same place as 155 wouldn't be at 155. It would have to go all the way around a circle back to 155. So to do this one, I'm going to add 360 degrees to the number 155. And so doing that would give me 515 degrees. 515 degrees would be one extra swing around the circle, but it would finish and stop at the same place as 155 degrees did. So if they want another positive angle, I would add 360. On this one, they want me to find a negative angle that's coterminal to 130 degrees. So for this one, I'm going to start with my 130, but here's how this one's different. I'm trying to find a negative angle. So instead of going clockwise, instead of going counterclockwise like I do with these ones, I'm going to be going clockwise. So I'm going to be going in the opposite direction. To figure out the first negative angle that's coterminal to 130 degrees, I'm not going to add 360. I'm going to subtract 360. And so doing so for this one gives me negative 230 degrees. So that would be the first angle going the other way, or the negative way, that would stop in the same place as this angle stopped here. On question number 14, I'm converting degrees into radians. And so remember, when you're starting with degrees and you're deciding which of the conversion factors you're going to multiply by, you're going to do the one with pi in the top. Remember, pi radians is the same as 180 degrees. So on both of these, when I multiply them by pi over 180, I'm really just multiplying them by the number 1, and then I'm going to simplify. You can do top times top and bottom times bottom and then simplify it afterwards. Or you can recognize that 30 goes into 30 once and 30 goes into 180 6 times. So changing 30 degrees into radians would give you pi over 6. Similarly, on question B on this one, to simplify this, I can do some simplification here and here. Both of these numbers divide by 30. 30 goes into 155 times, and 30 goes into 186 times. So simplified into radians, this one's going to give you negative 5 pi over 6 radians. You could also use the math fraction button on your calculator, and you could choose to simplify these using a different manner. But this way works just fine when you're switching from degrees into radians. On question number 15, we're doing the opposite, and we're switching from radians back into degrees. So to do that, I want the pi's to cross out on this one. So instead of multiplying by 180 over pi, or instead of multiplying by pi over 180, I'm going to multiply both of these by 180 over pi. Remember, pi radians is the same as 180 degrees. They're both halfway around a circle. So when you multiply something by something that's equivalent to 1, you're not changing the value of what this is, you're just changing the format that it's written in. For this one, pi crosses out with pi. And then you can do a little bit more simplification if you wanted to. You can also have your calculator. You could do top times top, bottom times bottom, and then use the math fraction option to switch it back into a fraction. 4 goes into 180 45 times, however. And so for this one, when I'm switching 3 pi over 4 radians, or negative 3 pi over 4 radians into degrees, I end up just doing 3 times 45. And so that gives me 135, but it's negative because this one was negative out here. So switching that into degrees would give me negative 135 degrees. And then for the next one, for B, same thing, pi crosses out with pi. 180 divides by 15 a set number of times. 15 goes into 15 once, and 15 goes into 180 12 times. And so changing this into degrees, 11 pi over 15 radians, when I turn it into degrees, is going to be 132 degrees. Question 16 through 21 asks you to graph the angle in standard form. So we're going to start by doing that. And then it also wants us to identify the reference angle. Remember that your initial side is always this positive x-axis right here. And so all of your angles are going to start from here. Quarter way around the circle would be 90. Halfway around the circle would be 180. 2/3 of the way around the circle would be 270. And then back to the start would be 360. And then it would just start all over again. So 135 is going to be halfway in between 90 and 180. So this is your 135 degree angle. So that's the angle that you're graphing. The directions to the question also want us to identify the reference angle. The reference angle gets made when you bring the terminal side of the angle either up or down. In this case, it's down to the x-axis. And then you're going to look at this angle over here. So for this one, 180 take away 35 would leave me here with my angle theta. I'll just call them all theta. So for this one, my reference angle would be 45 degrees. Your reference angles are always going to be positive numbers when you graph these. So for question 16, you would get 45 degrees for your reference angle. And then the rest of them would just continue in the same manner. 240 degrees is a little bit less than 270 degrees. And so the reference, or the angle itself, this is my 240 degree angle. But when I'm finding my reference angle, I'm going to bring the terminal side of that angle back up to the x-axis. And so this right here, I know I wrote it kind of small, but that's my theta that I'm trying to find. Theta had to go 60 degrees further than 180. So for this one, my reference angle for question 17 is going to be 60 degrees. This would have been 180, but this is where the angle stopped. So it had to go 60 degrees further than 180 to get to where it finished. 330 is almost all the way around. So this right here, that's my 330 degree angle. It had just 30 left to go to get back to 360, and so this remaining piece right here, that's my reference angle. So for this one, my theta, my reference angle, would be 30 degrees. And then last but not least, for number 19, it's 480 degrees. So this one's a little different. 360 degrees would get you one way all around the circle. And then you'd have 120 degrees left over to work with. So 120 is going to put you over here. that means that my original angle, my 480 degree angle, looked like that. And then when I'm finding theta over here, when I'm solving to figure out what my reference angle is for this one, it was 120. The reference angle gets formed by the terminal side of the angle on the x-axis, and so it would have 60 more to go. So for this one, my reference angle for 480 degrees, for this for question number 19, it would be 60 degrees. Questions 20 and 21 are just a continuation of the directions from the last page. So they're both negative though, so it is good to notice that these angles are going to be going the opposite way. So instead of going up and around 405, they're going to come down and around 405. So let's see, if it went around one whole time, that would get you back to 360. So 405 take away 360 leaves you with 45 left over. So it's coming down and around once, that would be 360, and then it's going 45 degrees past 360 again. So this is my negative 405 degree angle. And then I'm solving to find theta, which I kind of had to squish, but it's that reference angle right there. So for this one, my reference angle is going to be 45 degrees. Even though it's going in the negative direction, remember that your reference angles are always positive. For question 21, it's negative 120 degrees. So going negative means coming down this way. Remember, a quarter turn is 90, and then a half turn is 180. So 120 degrees is going to be sitting over here. This over here, that's my 120 degree angle. And so when I'm finding my reference angle for this one, it would have to go 60 more to get back to the x-axis. So for this one, theta, my reference angle, it's going to be 60 degrees. Questions 22 through 30 specifically indicate that you should be able to do them without using a calculator. So we're not just going to type cosine 30, sine 30 into our calculators. We're going to practice doing this without a calculator. The first thing you need to do is graph the angle. So 30 degrees means I'm working over here in quadrant 1. So that's my 30 degree angle. Once you have the angle graphed, you need to put the measurements on the sides. Remember, the side opposite the 30 is always 1/2. The side opposite the 60 is always the square root of 3 over 2, and then your hypotenuse on these is always going to be the number 1. So putting the measurements on the picture help you get started. Technically, you didn't have to label the 1/2 side, because for cosine, I'm only going to use adjacent and hypotenuse when I set up my ratio. So for this one, the cosine of 30 degrees is going to be equal to adjacent over hypotenuse, and so that gives me my answer to the question. The cosine of 30 degrees is equal to the square root of 3 over 2, because anything divided by 1 stays itself. For 23, it's the sine of 30 degrees, so I'm going to start by drawing the same picture, and then the same numbers go in the same places. On this one, you could omit the square root of 3 over 2, because you know for sine, you're only going to use opposite and hypotenuse. So the sine of 30 degrees is equal to 1/2 divided by 1. And so for this one, the sine of 30 degrees is going to be equal to 1/2. Question 24 asks us to find the sine of 45 degrees, and so 45 degrees is also located here in quadrant 1. Remember, for 45 degrees, it's the square root of 2 over 2, the square root of 2 over 2, and then 1. So those are your three side ratios that you're using for this one. To find the sine, I need opposite and I need hypotenuse. And so for this one, the sine of 45 degrees is equal to the square root of 2 over 2 divided by 1. And so the sine of 45 degrees would be equal to the square root of 2 over 2. By the way, your calculators can do these as approximations for you, but they can't do them exactly, so that's why we don't do them on our calculator. And then 25 starts to switch. So 135 degrees would be over here in quadrant number 2. Remember though, 135 degrees is this side. To find my reference angle, I have to do 180 take away 135. And so that would leave me with 45 degrees over here. This side's still going to be the square root of 2 over 2. This side would be negative the square root of 2 over 2 because it's coming to the left. And then my hypotenuse is 1. For tangent, I'm going to need opposite and adjacent. So the tangent of 135 degrees, remember I'm using 45 degrees as my reference angle, but I still use 135 when I write down my work. So let's see. its opposite, which is the square root of 2 over 2, divided by adjacent, which is negative the square root of 2 over 2. And so anything divided by itself is always 1. In this case, though, you're doing something divided by the negative version of itself. And so the tangent of 135 degrees is going to be equal to -1. Question 26, we're finding the cosine of 150. So 150 is over here also in quadrant 2. If this is 150 degrees, my reference angle would be 30 degrees. So this is positive 1/2. This is negative the square root of 3 over 2, and then my hypotenuse is always 1. So for this one, the cosine of 150 degrees would be equal to, for cosine, I need adjacent and I need hypotenuse. Negative the square root of 3 over 2 divided by 1. So the cosine of 150 degrees is going to be negative the square root of 3 over 2. The cosecant of 210, so 210 is down here in quadrant 3. 210 would be 30 degrees further than 180 degrees, so that's where I'm getting my reference angle from. This is -1/2. This is negative the square root of 3 over 2, and then always positive 1 for my hypotenuse. So remember, cosecant is the flip of sine. So instead of doing opposite over hypotenuse, I'm going to do hypotenuse over opposite. So I'll have to do that a little bit. Because the other thing you can do when you're figuring out cosecant, if you want to, is you can just figure it out as sine and get your answer for that question, and then you can flip it upside down. So that's going to be the way that I prefer to do this. So if I did the sine of 210 degrees, that would be equal to, let's see, opposite over hypotenuse. So the sine of 210 degrees would be equal to -1/2. Remember, though, I'm trying to find cosecant, and so cosecant is just the flip of sine. So I just need to flip the two of those upside down. So the cosecant of 210 degrees is going to be equal to -2 over 1, and then we would just choose to write that as -2. -405 degrees is going to come the opposite way. So remember, if it goes around once, it's 360, and then it would be going 45 past 360. So I would be working down here, and my reference angle would be 45 degrees. To find the tangent, I'm going to need opposite and adjacent. I'm actually not going to need the 1, but we just get in the habit of writing it. So for tangent, the tangent of -405 degrees is going to be equal to, let's see, tangent is opposite over adjacent. So those are the sides that I'll need to use for this one. So negative the square root of 2 over 2 divided by, oops, this one's actually positive, divided by positive the square root of 2 over 2. Anything divided by itself is 1. And then in this case, you're doing negative of something divided by positive of itself. So it's going to give you -1. On question 29, I'm finding the secant of -60 degrees. So -60 degrees means it's coming down here. It also means that my reference angle for this one's going to be 60 degrees. Negative the square root of 3 over 2, positive 1/2, and then positive 1. I could, for secant, let's see, for secant is the flip of cosine. So I'm not going to use opposite for this one. I'm going to use adjacent and hypotenuse. And so I'm going to do the same thing I did on the last one. I'm going to pretend like I'm finding cosine, even though I'm not. So that would be adjacent over hypotenuse. So the cosine of -60 degrees would be 1/2. But then I'm going to remember that I'm finding secant. I'm not finding cosine. And so secant is just the flip of cosine. So I'm just going to take the fraction and I'll flip it upside down or find its reciprocal. So the secant of -60 degrees would equal 2. And then the last one in this section is question number 30. It wants me to find the cosine of -330 degrees. So -330 would be almost all the way around the opposite way. It would just be 30 short. And so that's how I find that that's my 30-degree angle. And then I label my sides. For cosine, I'm going to need adjacent and hypotenuse. So the cosine of negative 330 degrees is adjacent over hypotenuse. So for this one, the cosine of negative 330 gives you the square root of 3 over 2, and it's positive because we're working in quadrant 1. Questions 31 through 34 want us to graph the angle in standard form and identify the reference angle. The difference with these is that they're being given to us in radians instead of in degrees. There's a couple different ways that you can think about this. For starters, you can change everything into degrees if you want to and just work in degrees, but that's not necessarily the most effective way of thinking about it. You want to remember that pi over 2 is halfway around the circle, pi is the full way around the circle. 3 pi over 2 gets you back here, and then 2 pi would get you back to where you started. 5/6, so ignore the pi for just a second, is a little bit less than 1. So if we were going to break this into sixths, it'd be 1, 2, 3. Here's 4. Here's 5/6, and then 6/6 would get you back to a full half turn around the circle. So when I graph 5 pi over 6 radians, this angle right here is my 5 pi over 6 radians part. To find my reference angle, I have to think about how many more sixth radians would get me back to this axis right here. And so if I label this axis, or if I label this angle theta for this one, my reference angle would be pi over 6. 5 pi over 6 would get me 5/6 of the way to here, and then I would need 1 more sixth to get me back here. Similarly, on the next one, it's being cut into fourths. So 1, 2, 3, 4. 4/4 would get me half the way around the circle. This would be 5/4, this would be 6/4, and so here in quadrant 4, that's where 7/4 would go. So this angle here is going to be 7 pi over 4 radians. And then to get back to the x-axis, for my theta, for my reference angle for this one, I would need 1/4 more to get me back to the x-axis. So my reference angle on this one would be pi over 4. Question 33 wants me to graph the angle 4 pi over 3 radians. So using my cutting, 1 pi over 3 would get me 1/3 of the way around. 2 pi over 3 would get me another 1/3 of the way around. 3 pi over 3 would get me here to pi radians. And so I would need to go 1 pi over 3 or pi over 3 extra. And so that would put me over here, and that's in quadrant 3. So again, my angle is the full 4 pi over 3. And then I'm being asked to identify my reference angle, and so my reference angle would be here. 4 pi over 3 goes 1 pi over 3 further. And so my reference angle for that one would be pi over 3 radians. And then lastly for this section, this one's negative 2 pi over 3 radians. So 1/3 of the way around would get me here, and then 2/3 of the way around would get me over here. So for this one, I would be working in quadrant number 3 as well. Remember, theta is not the angle that you're graphing. The angle that you're graphing, the negative 2 pi over 3 radians, is that part right there. So 2/3 would get me 2/3 of the way around to this side right here. And so I would need to go 1 pi over 3 or another pi over 3 further to get there. And so pi over 3 would be my reference angle for question 34 as well. Question 35 begins a series of problems. Let's see, for 35 to 40, it wants us to evaluate the trig expressions without using a calculator and with using SOHCAHTOA. The angles that are given to you in radians. So this is the same thing that we did previously, but before it was given to us in degrees, and now it's being given to us in radians. You are welcome to switch all of your radians into degrees and do the work that way, but most people don't find that that's the most effective way of doing it. Pi over 3 is 1/3 of the way around. You do want to practice, however, that pi over 3 is the same thing as 60 degrees because it's 1/3 of 180, and so that would be the same as 60. Remember, you can do the conversion here if that helps you understand that. If this is 60 degrees, that's the square root of 3 over 2, that's 1 over 2, and then my hypotenuse is always 1. And so for this one, the question is asking us to figure out what the sine of that angle is. So I'm finding the sine of pi over 3 radians, and so sine is going to be opposite over hypotenuse. And so the sine of pi over 3. Normally when you're doing radians, you go ahead and put this in parentheses just so that it's clear. So the sine of pi over 3 radians would be opposite over hypotenuse. And so the sine of pi over 3 radians here is going to be the square root of 3 over 2. In question 36, we're doing the cosine of negative 2 pi over 3 radians. So here would be 1 pi over 3, here would be 2 pi over 3. And remember, I'm going in the negative direction, which is why I'm going the opposite way. So if this is negative 2 pi over 3, my reference angle for this one would be pi over 3. Remember, pi over 3 is the same as 60 degrees. So opposite the 60, this would be negative the square root of 3 over 2 because it's going down. This would be negative 1/2. And then my hypotenuse is always positive 1. For this one, I'm finding cosine. And so for cosine, I need the adjacent side, and I need the hypotenuse. So the cosine of negative 2 pi over 3 radians is going to be adjacent over hypotenuse. And so it would give me, for 36, my answer for the question would be negative 1/2. 37 is the tangent of 8 pi over 3. So 1, 2, 3 pi over 3 gets me here. 4, 5, 6 pi would get me back here. 7, 8. And so as I go around the circle, 8 pi over 3 radians is going to put me back over here in quadrant number 2. 3 got me here, 6 got me here, 2 more got me here. And so my reference angle on this one is going to be pi over 3. Let's see. Over here, so pi over 3 is the same as 60 degrees. My square root of 3 over 2 is positive, but my 1/2 is negative. And for this one, I'm finding tangent. And so for tangent, I'm going to need opposite, and I'm going to need adjacent. So tangent is opposite divided by adjacent. Your teacher might have taught you to handle this a few different ways. When you're multiplying fractions, when you're dividing fractions turns into multiplying, and you're flipping this one upside down. Your teacher might have also just taught you that the 2's cross out here, but I'll show you the work for this one. So they're being divided, so I'm going to change it to multiply, and then I'm going to flip the second one upside down. The 2 that's in the bottom on the first fraction crosses out with the 2 that flips up to the top on the second fraction. And so then you're finished ultimately with that step, because when you multiply those together, you're going to do top times top and bottom times bottom. And so for question number 37, you get that the answer to the question is the tangent of 8 pi over 3 radians is equal to negative the square root of 3. All right, 5 pi over 4. So 1 pi, 2 pi, 3 pi, 4 pi over 4 would get you here. And then you would go 1 extra pi over 4 into quadrant 3. Oops, I kind of missed. I should go back to the middle. It's fine though. So this is pi over 4 past 4 pi over 4. And so that's my reference angle. Pi over 4 is the same as 45 degrees. So this is going to be negative the square root of 2 over 2, negative the square root of 2 over 2, and then 1. And I'm finding cosine. So for cosine, I need adjacent, and I need hypotenuse. So the cosine of 5 pi over 4 radians is going to be negative the square root of 2 over 2 divided by 1. And so for question 38, anything divided by 1 stays itself. So the cosine of 5 pi over 4 radians is going to be negative the square root of 2 over 2. And then 39 and 48 wrap up this section. So for 39, it's 11 pi over 6. So 1, 2, 3 pi over 6 would get you halfway. 4, 5, 6 pi over 6 would get you here. 7, 8, 9 pi over 6 would get you here. And then 10, 11 pi over 6 would be right here. And it would be 1 pi over 6 short of going 12 pi over 6, which would be 1 full revolution all the way around for the 2 pi. So let's see, for this one, pi over 6 is 30. So that's 1/2, but it's negative because it's going down. The square root of 3 over 2 and then 1. And for this one, I'm finding sine. So for sine, I'm going to need opposite. And I'm going to need hypotenuse. the sine of 11 pi over 6 radians is going to be equal to negative 1/2 divided by 1. Oops, I forgot the 11. And so for this one, the sine of 11 pi over 6 radians is equal to negative 1/2. And so that's your answer for question number 39, negative 1/2. And for question 40, it's 7 pi over 4, but it's negative 7 pi over 4, so it's coming in the opposite direction. So 1 pi over 4, 2 pi over 4, 3 pi over 4. 4 pi over 4 would get you back to 1, 5, 6, and then 7. So for this one, I'm working in quadrant 1. It's 1 pi over 4 short of being a full 2 pi revolution. That means that this is a 45-degree angle. So I'll label my sides, excuse me, and then for this one, tangent of negative 7 pi over 4. For tangent, I'm going to need opposite, and I'm going to need adjacent. So opposite over adjacent. And then there's a couple different ways that you can handle this. Anything divided by itself is always 1. If you wanted to show out the work, your first fraction stays the way it's written, and then the second fraction flips upside down. But these cross off and these cross off, and so you're left over with just 1. So we would say that the tangent of negative 7 pi over 4 is going to equal, and they're both positive. And so in quadrant 1, all of your trig ratios are going to be positive, so this works out to be positive 1. The last question before we get to the graphing says, for question 41, use a calculator to evaluate the trig function of the angle that's given in radians. If necessary, round your answer to the nearest thousandth. So notice that this one has a pi and this one has a pi. They don't have to have pi's for you to know that they're in radians. They just need to not have degree measures. And so because both of these don't have a degree symbol next to them, I know that I'm working in radians. Depending on what mode your calculator was in last, so mine's in degree mode, I have to go ahead and switch it back to radian mode. And I know it's in radian mode when I look up here and it says radian at the top. So there's no work to show for these ones. You're just typing them into your calculator. So the sine of 5 pi divided by 12 radians, and then rounded to the nearest thousandths. So I'm doing 3 decimal places. So this would be 0.966, and it's positive. And that's all you can do on that one. So that's your answer to the question. You're recognizing on this one that the reference angle wouldn't be one of the 3 reference angles that you know how to do. So the only way to do these ones would be to do the work on a calculator. And for B, you're finding the cosine of 5.2 pi radians. So cosine of 5.2 pi radians, and enter. And then you're rounding it to 3 decimal places. So negative 0.809. And again, there's no work to show for this one. Again, you're just recognizing that there's no reference angle that could help you find this. So the only way you can do it is by typing it into a calculator. The last part of the review concludes with a section on graphing. So for questions 42 through 50, the directions to the questions say to graph the following trig functions, and it wants us to make sure that we identify and label the period. I'll also make a note on each of these about amplitude just so that you can practice that as well. So 42 is y equals 2 sine x. So you'll remember that sine always goes through the middle. Sine has, as long as there's no horizontal compression happening, sine has zeros at pi and 2 pi, and then at negative pi and negative 2 pi radians. And then at the pi over 2's, so here and here, normally it would go up to 1, but this 2 out front creates a vertical stretch by 2. So instead of just going up to 1 here, it's going to go up to 2, and then instead of just going down to 1 here, it's going to go down to negative 2. And then on this side, it would be the opposite of that. So when I graph this trig function, it just looks a little bit wavier than it did. So the amplitude on the waves have changed. Remember that the period of a graph is how long it takes for it to get back from where it started to where it started. So from 0, it goes up and then back to the middle, and then down and back to the middle. So 0 up to 2, 0 down to negative 2, and then back to 0. You can count from any 2 points on your graph, though. So when you count the period of a graph, you're just counting from where it gets from where it started. So some people like to do from the top to the top or from the bottom to the bottom. So from negative 3 pi over 2 to positive pi over 2, the period on this function would be 2 pi. And so as long as there's no horizontal compressions, your period on your sine graphs is always going to be 2 pi. Same actually goes for cosine. The only thing on this one that would be a little bit different is the amplitude. Remember, the amplitude is this distance right here. And so for this graph, because of the two stretch out front, the amplitude on this graph is going to be positive 2. And again, on sine and cosine, your amplitude will be whatever the number is out front, because that's telling you how much the graph is being vertically stretched by or vertically compressed by. 43 asks me to graph y equals negative sine of x. So my zeros are going to be in the same place on this one. And again, I know that because there's no horizontal compression happening. There's no number in next to the x, so it's not changing how fast the graph is waving. The only thing different on this one is negative out front. So normally at pi over 2, it would go up to 1, but if it's negative, it's going to go down to 1. Oops, that's in the wrong spot. So at pi over 2, normally it would go up to 1, but it's going to go down to 1. And then at 3 pi over 2, normally it would go down to 1, but it's going to go up to 1. And then over here, again, it would be the opposite. So this graph doesn't have a vertical stretch or a vertical compression happening to it. The only thing that happened was a reflection. So instead of going up from 0, 0, it goes down from 0, 0. The period of a graph is however long it takes it to repeat itself, so to get back to the place that it started. And so for this one, there was no horizontal compression, so my period for this graph is going to be 2 pi. And then there was no number out front with the negative. And so remember, your amplitude is the distance from the midline to either the highest point or the lowest point. And so for this one, my amplitude is 1. An amplitude of 1 is the regular amplitude for sine or cosine. Notice how even though it's negative, you don't see that the amplitude is negative 1 because you're measuring distance, and distance is always measured with positive numbers. All right, so 44 actually has two things happening on it. The first thing that you'll notice is that there's a 3 out front. So I'm going to be going up to positive 3, and I'm going to be going down to negative 3. But the other thing that's happening right here with this 2, so there's a horizontal compression happening. Normally, sine goes through the middle, and so even with a horizontal compression, sine is still going to go through 0, 0. And then normally it would go up here, and then back to 0, and then down here, and then back to 0. But what this 2 does, it's a horizontal compression by a factor of a half. It means that it's going to get back to 0 twice as fast. So that means that the 0 that would have been here comes over here half as far, and then the 0 that would have been here comes over here half as far. So when there's a 2 inside with the x on sine, it means that your graph is going to be hitting 0 every pi over 2 units. So it's going to have a shorter period because the waves are going to happen more quickly. Halfway in between 0 and 0, it has to get up to 3. And then halfway in between this 0 and this 0, it would have to get down to negative 3. And so that pattern for this one would just ping pong. Oops, that's in the wrong. No, that's in the right spot. It would just ping pong back and forth. And then over here, it would be the opposite. So down to negative 3 up to positive 3, and then down to negative 3. That one's going to go over the problem a little bit. So there's two things acting on this problem. The first one is the 3 is stretching it vertically, so that's what's making it look so tall. The second thing that's happening on this graph is the 2 that's on the inside is compressing it, and remember, that shortens the period. So the period on this graph, you could measure from here to here, or you could measure from here to here, or any of the 2 points that are in the same spot. The 2 that's on the inside next to the x compresses the period by half. So instead of the period being 2 pi, for this one the period's going to be pi. The other thing that changes on this graph is the amplitude. And remember, it doesn't matter where you measure the amplitude on a graph. I kind of feel like I'm measuring them all in the same place. But for this one, the amplitude, or the distance that the graph goes above or below the midline, on this one it's 3. So the amplitude is always going to match the number that's out front on sine or cosine. And then when there's a number in here, it's going to make the period be shorter. So if this was a 2, it cuts it in half. If this was a 4, it would cut it into 4 pieces. And so we'll see an example of that later on. What the first 3 graphs in the graphing section had in common is they were all sine graphs. On example 45, it gives us a graph of cosine. So the big difference between sine and cosine is cosine doesn't go through the middle. Cosine usually goes through positive 1, but there's a negative out in front on this one. And so that's going to make my graph be a little bit different. Instead of going through +1, this cosine is going to go through -1. So on your cosine graphs, the number that's out front tells you what your y-intercept is. That's a good connection to make here. And then it goes back to 0, and then it would go up to +1, and then it would go back to 0, and then it would go to -1. The tricky thing for most students about cosine is that it has the same pattern, or almost the same pattern as sine does. It's just shifted over a little bit, so back to 0 and then down to -1. It can be hard sometimes to look at a graph and tell whether it's sine or cosine until you get practice with it, that is, because I can tell right away that this is not a sine graph because it doesn't go through 0, 0. It doesn't go through the middle here. Without a horizontal compression happening, my period, or my amount of time it takes for the graph to get back to where it started on cosine, is 2 pi. And then the number out front on this one it's negative, which is why it flipped upside down and caused that reflection. But remember, this is your amplitude. And even though it has a -1 out front, we say that the amplitude of this graph is +1. We measure distance in positive numbers. For 46, there's no negative out front. This is cosine. Normally cosine starts at 1, but this one has a 3 out front, so it's going to stretch it up. So it's going to start here at +3, and then come back to 0, and then it'll go down to -3, and then come back to 0, and then go back to +3. And then over here, it's just doing the opposite pattern. So for question 46, the period of the graph hasn't been adjusted at all. The only thing that's been adjusted on it is the amplitude. So for cosine right here, you can see pretty clearly that the period of your graph is 2 pi because it takes the regular 2 pi units for it to get back to where it started. The only thing about this one that's different is the amplitude. You can measure amplitude on the top or the bottom of the graph. It doesn't matter because it's always going to be positive, so I'll measure it over here. So for this graph, the amplitude is the number 3, and it's going to match this number out front. So it's 3 because it's going 3 below, or it's going 3 above that midline. This last cosine graph is one that students might think is a little bit tricky. So it has a negative, so there's going to be a reflection, but then it also has this 4 in here. So let's see, regular cosine usually starts at +1, but this one's flipped, so it's going to start at -1. And then regular cosine would go 0 and then up to +1 and then back to 0 and then back down to -1. But this 4 means that it's going to get through that rotation or that revolution 4 times as fast. So it's going to get back to -1 at pi over 2, and it's going to get back to -1 at pi, and it's going to get back to -2 at 3 pi over 2, and it's going to get back to -1 at 2 pi. Halfway in between each of these numbers, there would need to be the corresponding maximum. So here, and here, and here, and here, this graph would hit high points. And then that would mean that there were zeros halfway in between halfway. So there would be a 0 here, and a 0 here, and a 0 here, and a 0 here. And so it would continue to follow that pattern. So there's lots of waves in this one because the period has been shortened by a 1/4. It's been horizontally compressed by a 1/4. The pattern over here would continue. So at all of the important numbers, it would hit that -1, again, because it was a reflection. Halfway in between each of these, it would hit that +1, and then here in between is where the zeros would be located. And so there would be a 0 every, what would that be, pi over 2, so pi over 4, so pi over 8. So there's a 0 happening every pi over 8 units. The points are what's important to graph on this before you start trying to draw in the waves, because you want your graph to go through the important values. And so the maximum, minimum, and the x-intercepts are the most important values on this graph. Labeling the period's how long it takes it to get back to where it started. So for example, from here to here, my period on this graph is shortened. It's only pi over 2 because it only takes a half of a pi radian to get back to where it started. And then your amplitude, remember that's this distance. And so this one had a negative out front, which changed where the y-intercept was, but the amplitude on this graph is still 1 because it rises 1 above or 1 below that midline. The biggest thing to remember about the graphs of tangent is that they're different. So for question 48 and for question 49, tangent has zeros at 0, at pi, and at 2 pi, and then also at negative pi and at negative 2 pi radians. Tangent is undefined, so there are vertical asymptotes located at the pi over 2's. And so these are the places where tangent is not defined or does not exist. So once you have those dashed lines drawn in on your graph, then you can put in the other important points. Tangent is 1 at pi over 4 and negative pi over 4. It's at negative 1. And so then that pattern will continue on all of these. Now what you want to be careful of, though, is that these 3 points that I'm drawing in each of these places look like they're in a straight line, but they're not. And by typing in more values of pi for tangent, you would be able to see that the graph bends. They kind of look like x cubed, except it has nothing to do with that. But if you want to try to remember that that's what they look like, you might find that helpful, just kind of in your memory getting ready for the test. Okay, and so tangent isn't a connected curve like the other graphs were. Tangent is these separate pieces that repeat themselves. Tangent repeats itself. Let's see, I'll measure it here. So the regular period for tangent, when there's no kind of compressions acting on it, is just pi. So it's half of the period for the other graphs. And then you should also make note that there's no amplitude when it comes to tangent. You can stretch a tangent graph, but you can't discuss its amplitude because it increases and decreases without bound above and below that midline, so you can't talk about how high and how low it goes. The difference with the second graph is just the direction. So it's still going to have zeros at all of the pi's, and then it's still going to be undefined. So these are my vertical asymptotes. And remember, I draw those in with dashed lines. So at all of my pi over 2's, it'll have dashed lines. And then the only thing about negative tangent x that's different is instead of going up to positive 1 and down to negative 1, they flip and they go in the opposite direction. So instead of going up and to the right and down and to the left, I'm going to go down and to the right and then up and to the left. And so when I draw in my graph for tangent, I'm drawing it in so these guys look backwards compared to the one up above. There's no discussion of amplitude when it comes to tangent because, again, they increase and decrease without bound. But we can label the period on this one as well. So the period is how wide these are. And so for this one, my period for this graph is pi radians. That's how long it takes it to repeat. And finally, last but not least, question number 50. This one has a 3 out front. So it's not causing a change in the period, so I can go ahead and put my zeros on the graph where I expect them to be. And I can go ahead and put my vertical asymptotes on the graph for tangent where I expect those to be. There we go. There's no negative out front, so there's no reflection. So the only thing that's going to change about this one is that normally on tangent it goes up and over 1 and up 1, and then over 1 and down 1. But on this one with the 3 out front, it's going to stretch it. So these points are going to be 3 away. So it's going to go over 1 and up 3, and then over 1 and down 3. Again, when you graph tangent, you just want to be careful because these points are in a line, but it's really important that when you draw them, you don't just draw straight lines because that doesn't follow the pattern or the rule for tangent. So they bend, and they bend pretty substantially. Here, I'm just drawing a sketch of the graph, so I'm not worried too much about being 100% precise with the location of these. I'm just drawing them so that they follow the pattern of the graph for where tangent is located. The 3 stretched how far away these points were from each other. Again, we don't say the amplitude on this graph is 3 though, because we don't discuss amplitude with tangent, but we can discuss the period. And because there was no compression horizontally, the period for this graph would also be pi.